Okay, we are first going to start out with a trig example. And then we're going to do what's called incomplete substitution. Okay. When you have multiple trig functions in your integral, you have some options. What is one option?
Do them separately.
What do you mean?
Well, like, you could do the cosine squared antiderivative and then the sine squared, like just each has their own part.
You have an antiderivative for cosine squared?
Probably not.
No. And we can't do things like separate. Like if it's all in a fraction, it's either all or nothing. We either have something for it or we don't. Okay, what did you say? Okay, what is sine over cosine? And what is 1 over cosine? What's the antiderivative of tangent times secant? Okay. Don't feel like you're pigeonholed to doing a substitution problem just because we have more than one function thrown up there. Now, would it have worked to do u substitution? It actually would have. Because we could have done u equals the cosine of x, which means du is how about negative sine dx? So we could have done negative integral of 1 over u squared du, which would still have gotten us to secant x plus c, just a little bit longer route. But it doesn't matter, right? We can still get there no matter what. Okay. Okay, how about one where we don't have that? Okay, here's our next trig example. Do we have a composition? Mm-hmm. We do. And our trig identity is going to help us here? Not really. Okay. There's not a whole lot we can do. However, since we have a composition, we may be able to do u substitution. If we wanted to try u substitution, which part would we try to set u equal to? Okay, what's under the radical, right? What also makes this nice is we know that sine and cosine have a derivative relationship, so hopefully this will work out for us, right? If u is 1 plus sine of x, then du is cosine of x dx. And do we have cosine of x dx in our integral? We do. So this becomes u to the 1/2 du. Look how simple that. This antiderivative is u to the 3/2 times 2/3 plus c. So we change u back to its function in terms of x. We have 2/3, the quantity of 1 plus sine of x to the 3/2. All right, so we're feeling good? Okay. When you have trig functions, look for opportunities to do identities. You don't have to, but at least look to see if something pops out at you. if it doesn't give you something nice, look to see if there's a way to do u substitution. Now, I want to talk about something called incomplete substitution. Okay. Sometimes we can use u substitution, but maybe there's like a little something extra left over. Okay. What do I mean by that? I'm just going to go straight into an example. X square root of 2x minus 1 dx. Now, when we have a composition, we usually look to see if there's that derivative relationship happening. So if there's an x on the outside, we would be hoping for like an x squared on the inside of a function. Do you see what I mean? But that's not happening, is it? Okay, so we have something kind of funky. Now, it's not completely bad news because we can still finagle our way through a substitution, okay? Since we have a composition, let's go down our normal path of what's inside. Let's set that equal to u. So u would equal 2x minus 1, which means du is 2 dx. Okay, so we know that 1/2 du is equivalent to dx. So we can come over here and we can replace dx with 1/2 du. And we can replace this square root with u to the 1/2. But then we still have that pesky x. Our ship totally sunk.
Could you sub x for like a version of u?
Could we sub x for a version of u? If we know that u is 2x minus 1, could we make this u plus 1 over 2 equals x and sub that in, and now we're all the way in terms of u. How did I get that? Right? I added 1, divided it all by 2. So instead of x, we can write u plus 1 over 2. And now we have everything in terms of u du. Okay? That x left over is why I call this incomplete substitution. Now, this version right here is not something we can just, boom, take the antiderivative of. We're going to have to rewrite it just a little bit so that we can use the power of rule. Okay, so something that you don't have to do, but something that I see is I see that there's this 2 here, and I can maybe just group it out here with this 1/2 to make it a 1/4, and I'm no longer worried about constants inside my integral. And then we can distribute that u to the 1/2 through. So this would become u to the 3/2 plus u to the 1/2 du. If you leave that 2 in the denominator inside, it's not going to change your outcome. Sometimes it's just easier to work with our constants on the outside. Are we okay with these right here? Next.
Yeah.
Yes? Okay. So we have 1/4 times u to the 3/2. That would go to u to the 5/2 times 2/5. Plus u to the 1/2 would go to u to the 3/2 times 2/3 plus c. So now to write my final answer, I'm going to go ahead and distribute that 1/4 while switching back to in terms of x. So my final answer, I would write 1/10 2x minus 1 to the 5 halves plus 1/6 2x minus 1 to the 3 halves plus c. What can I clarify for you about what we just said? Next.
Oh wait, never mind. This gives you for a second, I was gonna be like, why is it equal to 3 half? But
Yes. Yes. Okay. And if you kept the 2 there, it's not going to change the outcome. It just makes it a little bit smoother. In my opinion, you may have a different opinion, and that is fine. All right, so we have about 5 minutes left. Let's do one more just so you can see another one. And then we'll go from there, okay? Okay, so we have a composition, and I know that there's something in the numerator and something in the denominator, but when we have a fraction, looking at the denominator is sometimes a good place to start. Now the square root itself is going to make our du tricky, so just going in the square root and letting u equal x plus 4 would be more helpful, so then we don't have to worry about that radical hanging over in the derivative. Okay. Well, if we let u equal x plus 4, then du is dx. That's a sweet substitution, right? So our denominator is the square root of u, and dx is du, but we still have 2x plus 1 in our numerator, okay? This is why we call it incomplete substitution. I can't have x's and u's in our integral with du. So we can come over here, and we know that u minus 4 means the same thing as x. So we can change this to 2 times u minus 4 plus 1. Okay, now let's do a little bit of algebra before we even attempt that derivative. That numerator is the same thing as 2u minus 7. And then that u to the 1/2 in the denominator is the same thing as if we multiply by u to the negative 1/2, like if we bring it upstairs. So the integral that I would rewrite this to make my life a lot easier, and really this probably is your only option, is 2. This would become, if this is u to the first times u to the negative 1/2, that would become u to the 1/2 minus 7u to the negative 1/2. So when we take our antiderivative, u to the 1/2 goes to u to the 3/2 times 2/3 minus 7 This becomes u to the 1/2 times 2. And then we can replace our u's back with x plus 4. Make sure you get them back to x's. After all of this work, I would really hate for you to leave them in terms of u, okay, and make that point of getting back to the x's. So if you are a senior, just show up tomorrow and do this homework, okay? I will be available to answer questions as we work. If you are a junior, I'm sorry, I didn't plan on having to use class time, but that's how it goes. And so juniors, either do your homework tonight or do it tomorrow night, but come Wednesday with it done. And then we'll get review worksheets on Wednesday for our quiz Thursday. I like a Thursday quiz better, all right, because you get more time. It is a National Honor Society meeting day. Yes, so if we can talk Wednesday about, like, if you have questions, when would be a good time to come in, okay? Yeah, so there's your first reminder about the meeting.